Yeah, thank you very much. Welcome to my talk on our analysis of the W3C web payment APIs. My name is Guido Schmitz, and this is joint work with Quoc, Pedram, Hosseyni, Ralf, Küsters, Nils, Wenzler, and Tim Würtele. So if we look at the current state of online shopping, in particular the checkout and payment process, frankly speaking, this is a bit of a mess. Users are confronted with various different forms. Every merchant does things slightly differently, and in the end, users type in their payment data in some random form which they might have never seen before. This is where web payment or the web payment APIs come into play. So this is a new effort with the goal to provide a standardized, faster, more convenient online checkout process with improved security and privacy. And the general idea is that the browser gets a new core native feature that acts as a broker between merchants, payment providers, and users. And users perform the checkout process in a standardized, trusted user interface that is rendered outside of the context of the merchant's website. So in this talk, I will first give you an overview on the protocol behind this new web payment standard. Then I will give you a brief introduction in the method that we use to analyze such standards. That's the web infrastructure model, or WIM for short. And then I will give you an overview of our analysis and our results. So let's start with the web payment APIs. So actually, the web payment APIs is a set of various specification documents. They specify, for example, an API for the merchant, an API for payment processors, and various other spec documents cover the various metadata formats that are used in the payment process. This is already implemented by all major browsers and supported by many payment providers, most notably the big tech companies, for example, Google Pay or Apple Pay. So how does this process work? So here we have the user's browser. In the browser, we have the website of the merchant. Then we have this new payment component in the browser, which also provides this trusted user interface. And in the background of the browser, we have service workers. So service workers is nothing specifically for web payment. It's a general feature of the web. You can think of like JavaScript applications that run in the background of your browser, and they are installed by websites. So a website can install a service worker, and this then continues running in the background. And in the context of web payments, we have a special kind of service workers. These are the payment handlers, which are installed by the payment providers, for example, Google Pay. So, how does the protocol behind that look like? We start with the user on the merchant's website. The user has filled her shopping cart and starts the checkout process. Now the merchant creates a so-called payment request. That is a document that contains all the information about the checkout, the shopping cart contents, shipping methods available, and also the payment methods that are accepted by the merchant. The merchant now hands over control to the new browser component. The browser checks with all the installed payment handlers which ones are available to provide the accepted payment methods by the merchant. And then the user is presented with that trusted user interface where the user can enter details like shipping address or select a payment method, and then later on also performs the actual payment. So now let's assume the user has filled out that form, or the browser can also pre-populate that based on the user preferences. The user clicks on the pay button, and now control is handed over to the selected payment handler. Now the payment handler processes this payment. Probably it will also connect back to the back end of the payment provider. So this part is proprietary to the respective payment providers. The payment handler can also display certain dialogues to the user for authentication or further verification of the payment. And once the payment has been performed, control is handed back to the browser component, along with some other data, like, for example, a proof of payment or other data, but that's up to the payment provider to specify. Now the browser combines that information with the data that the user entered previously, like the shipping address, and hands that back to the merchant. And the merchant can now verify that information and complete the process by telling the browser component that the merchant is happy. The browser displays a success message to the user, and we are done. Okay, so how do we analyze this? So our approach to analyze such web standards is the Web Infrastructure Model, or WIM for short, which we first presented here at Security and Privacy in 2014, and we improved the WIM also in the subsequent publications. So what is the WIM? The WIM is a detailed, comprehensive, and precise formal model of the web infrastructure, and in fact, it's the most comprehensive model of the web infrastructure to date. It summarizes and condenses relevant standards, and as such serves as a solid basis for security and privacy analysis of web standards and applications. And furthermore, it can also serve as a reference model for developers, researchers, and also for teaching. So let's look at the high-level picture on how analysis with the WIM work. So we have a foundation, which is the formal description of the web that contains definitions, for example, for browsers, but also for communication like HTTP. And on top of that, we build an application-specific model reflecting the aspects of the application that we want to analyze, or in the case of standards, generic implementations that exercise non-deterministically the whole feature. So these two layers then form the complete model, and using this formal model and the formal language that we establish with that, we can then precisely specify security properties. And of course, we then can carry out a proof to check if these security properties actually hold. And if that proof holds true, then we know that for all attackers captured by this model, the security property is always satisfied. And this is quite a strong result, because by this we can even exclude unknown classes of attacks. Of course, a proof can also fail. In this case, we can analyze why did the proof fail and use that insight to derive attacks. But more importantly, we can also use that knowledge to develop fixes. We can then reflect these fixes into the model and then essentially rinse and repeat that process until our proof finally goes through. So let's take a closer look at the foundation of the WIM itself. So what is defined there? We have a network, and we have an unbounded number of processes, like, for example, browsers, web servers, or DNS servers, and they can interact with each other by exchanging messages over this network. We can also have web attackers. They participate in the network as any other process, but we also can have a network attacker who controls the whole network and can block, intercept, and spoof messages as it likes. And this is a Dolev-Yao style model. That means that the messages are terms, so our reasoning is based on symbolic derivability. That essentially means we consider the crypto primitives to be perfect and focus on the actual interactions between the different components. But the WIM is not just yet another standard Dolev-Yao model, but the distinctive feature is that it covers web features and is close to web standards. So to give you a little taste of the level of detail that the WIM covers, let's have a look what our browser model includes. So our browser model includes precise handling of DNS, HTTP, and HTTPS messages. We have a detailed window and document structure. Inside each document, we can have scripts. Scripts can either be honest, in that case, they model application-specific behavior, or they are malicious. In that case, they non-deterministically take any action they could possibly perform. We also have features like web storage and cookies, cross-window browser messaging and XML HTTP requests, and also many other features like handling of various message handlers, redirections, and so on. So how do we use the WIM now to analyze the web payment APIs? So first of all, we need to include the features that are used in web payment in our generic model. So we have to extend this part of the WIM, most notably the browser. So we include a new feature to facilitate service workers and also browser internal events to communicate with these service workers. So these two contributions are also of independent interest because they are not specific to web payment. And of course, we include the web payment APIs themselves in our browser model. Our application-specific model contains generic merchants and generic payment providers that non-deterministically exercise the web payment APIs. As security properties, we identified 2 integrity properties. One is that a payment or payment that is performed by a payment processor always has to correspond to the user's intent, namely to pay amount X to merchant Y. And the other one is uniqueness of payments, roughly speaking, that a payment should never be executed twice. You might have guessed it by now, our proofs didn't went through because we identified several flaws in the specifications and discovered 2 severe new attacks. One is the double charge with retry attack that allows a malicious merchant to essentially execute a payment more than once. So that obviously breaks uniqueness of payments. And the other one is based on ambiguous payment method data that allows a malicious merchant to add hidden fees which are not displayed to the user during the payment process, but are later included in the actual payment themselves. So to give you a small impression on how these attacks look like, let's take a closer look at the double charge attack. So this figure you have already seen previously. That's the standard web payment flow. The main difference here is we now have a malicious merchant, and we assume that we have at least 2 payment handlers installed in the browser. So the user starts the checkout process as usual, and at some point selects a payment method that leads to the selection of payment handler A. And then the whole flow continues as usual. The user confirms the payment processor processes the payment, and then it runs through until the very last step. And here, the merchant tells the browser, no, I'm not happy with that. There might be an error. So there is a retry mechanism built in the web payment method that allows a merchant to trigger or raise an error at this stage. And the merchant can freely specify an error message that is displayed within the trusted user interface. So the user is still in that trusted user interface, in that payment context, and gets displayed an error message that is essentially set by the merchant. And the merchant in this case would set an error message like, there's an error, please use a different payment method and try again. So while the user is still within that context, the user might easily believe that this message is true and might select another payment method that leads to another payment handler B. And now the payment gets processed again, and the user pays again for the same in the same checkout process. So that obviously breaks uniqueness of payments. So we reported these findings to the W3C working group. They confirmed these attacks, and also we proposed fixes to them. And they opted for one fix that we proposed that is quite straightforward and doesn't change the protocol at all. So essentially, we say when we run in such a retry flow, then a change of the payment method is not allowed anymore, and when the user tries to change the payment method at this stage, she gets displayed a certain error message by the browser that this is not allowed, and she should check whether some other payment has gone through. So, as I mentioned, we reported these findings to the W3C. They confirmed the findings. They adopted the fixes that we proposed, and these fixes we then reflected back in our model and run the proof again. And this time the proof went through. So actually the integrity of payments properties hold true for the fixed model. Okay, so to conclude, we performed the first in-depth and first formal analysis of the W3C web payment APIs. For this, we used the web infrastructure model, which we had to extend significantly, and in particular, we added features like service workers, which are also of independent interest. We identified several flaws in the specifications, found attacks, and also proposed fixes which have been adopted by the W3C. And also, we ran a security proof on the fixed standard and showed that the standard is actually secure. With this, I'm happy to take your questions, and thank you very much for your attention.
Thank you very much. So if anyone has a question.
Thank you. So, in your model, I think it was slide 11, you described that attacker is either a process or it's controlling the whole network.
Yes.
Can it actually take over another process to some extent?
Yeah, that is true. So what I didn't mention that our model also features dynamic corruption, so the adversary can at any time take over any process.
Thank you. Thank you.
Any other question? Oh, thank you.
To clarify, a payment handler is a payment method? Okay.
Not quite. The payment handler is a process that can process several payment methods. So the payment method can be, for example, credit card payment, or but it can also be something like a PayPal transaction. And the payment handler is one instance or piece of software of a payment provider which can process such transactions.
I don't see any online questions, so I'm going to ask one of my own. You mentioned that the model is a W model, okay, not a standard one. Pure interest, would it be possible to encode your model within one of those automated tools like Tamarin and ProVerif, or there's actual feature that prevents you to use an automated tool? Because I think in your paper you proof it on by hand. Right.
That is correct, and that's a very good question. So at the moment, the WIM is a pen and paper model, but we are currently working on a new approach for mechanized analysis that is based on F-star. So for this, we created a new framework called Dolof-Yarostar, which is a new mechanized framework for protocol analysis, because one problem with the WIM is we essentially don't restrict the model itself. So we can have unbounded data structures, recursive data structures, unbounded loops, and these are features that the existing tools like Tamarin and ProVerif sometimes struggle with. So when we created the WIM, at first we didn't want to restrict ourselves by any of these limitations of these tools. That's the reason why we opted for a pen and paper model back then, but we are working on the mechanization because that's definitely a very valuable feature to have.
Thank you. One last question.
Hi, thank you for the talk, very good. I was wondering, can you actually enforce arithmetic contracts or conditions in the analysis? Do you actually encode any arithmetic?
Sorry, I didn't read your question. Can you speak up a bit, please?
Of course. Do you actually encode or have to encode any arithmetic in your checks? Because ProVerif cannot do arithmetic, for example. I was wondering if you actually added arithmetic for any kind of...
algebraic features, you mean? Sorry, I get some echo over here.
Oh, okay, sorry about that. So I was just wondering if you encoded arithmetic.
Arithmetic. That's a good question. So I think the model can be easily extended to include arithmetics, but at the moment we don't have that.
Thank you very much. We can thanks again the speaker for this very nice talk.